Hello viewer, today we will study about the Euclid algorithm. I am Ajay Kumar, Assistant Professor, Department of Computer Science and Informatics, Central University of Himachal Pradesh. So, in this lecture we will study about the Euclid algorithm. Euclid algorithm generally based on the GCD. So, first you have to know the Euclid algorithm for GCD, and before going to the start of Euclid algorithm, you should know the basic concept of GCD. GCD means greatest common divisor, okay. And the next content is Horner methods for polynomial evaluation. So, greatest common divisor GCD. What is the fundamental concept of GCD? So, first example, when we want to GCD of 12 and 33. So, first we have to know the what are the divisor of 12. So, we have to start from 1. So, 1 divide 12, 2 divide 12, 3 divide 12, 4 divide 12, 5 doesn't divide 12. So, you have to start from 1 to the element that is 12. You can go till half of that element also. Okay. So, 1, 2, 3, 4, 5 doesn't divide 12, then 6, 7, 8, 9 doesn't 10, 11 does not divide 12. So, at last is the element itself. So, 1 and the element itself by default divisor are there. In case of 33 also you can see 1 and 33 by default divisor, and the rest element you can go till half. 33, half of 33 is like you can say 16. Okay. So, 1, 2, 3, 4, 5 you can check it from 1 to half of, you can use the for loop also. So, what are the common divisors? 1, 2, 3, 4, 5, 6, 12 and 1, 3, 11, 33. What are the common divisor? That is 1 and 3. And what are the greatest among the common divisor? That is 3. So, GCD of 12 and 33 is 3. Next example you can see what are the GCD of 25 and 150. Again same fundamental rule, you have to start from 1 and 25, 1 and number itself already divisor, and what are the rest of the divisor, you can go from 2 to like half of the element. So, 2 doesn't divide 25, 3 doesn't divide 25, 4 doesn't divide. So, 5 only one divisor is after 1 and number itself, that is 5. In case of 150, that is 1 and 150 by default divisor, and the rest of the divisor you can see 2 divides 150, 3 divide 150, 5 divide 150. So, what are the common divisors? So, common divisors are 1, 5 and 25, and what are the greatest among the common divisor? That is 25. So, GCD of 25 and 150 is 25. Next example that is 13 and 31. So, what are the divisor? By default divisor, that is 1 and 13, and in case of 31, 1 and 31, both are the prime numbers. Okay. So, when we want to find the GCD of number that is already prime, so only one common divisor will be there, that is 1. So, 13 or 31 both are the prime numbers. So, co-prime, that is 13 and 31 is known as the co-prime. So, at the case of co-prime, that is the, if you want to find the GCD of prime numbers, generally you got 1. So, GCD of co-prime is equal to 1. What is the fundamental concept of Euclid algorithm behind the GCD? So, GCD of two numbers is the largest number, you already seen in previous 3 examples, that divides both of them. Okay. So, here you can see GCD, that is 25, 25 divides 25 and 150 also. Okay. So, GCD means the number which divides both the numbers. So, a simple way to find GCD is to factor. This is the another method you can find the GCD, that is if you want to find the GCD of 36 and 60, here you can see these all are the factors of 36, 2, 2, 3, 3, and the factors of 60 is 2 to the power 2, 3 and 5. So, if we multiply the common factors, that is 2 to 3, and we can get the 12. So, this is the another method. So, what is the Euclid algorithm for GCD? This is not the Euclid approach, this is the Euclid approach. Here if A and B both are number, generally we consider A is greater than B. So, in this case if we divide A that is 33 is divided by 12, what will be the quotient and remainder? Quotient will be, if we divide 33 by 12, so 12 to the that is 24, and if we subtract 33 minus 24, that is we can get the 9. So, 9 will be remainder and 2 will be quotient. So, what will be the next step? In next step, that number B will act as A and the remainder will act as b. Again we will do the same things, we divide 12 by 9 and we can get the quotient and remainder respectively, and in the same way again the value of b is assigned in a and the value of remainder is assigned in b, and again we can divide 9 by 3 and we can get the quotient 3 and remainder 0, and if we assign the value b to a and remainder is 0, when you have to stop, when b becomes 0, that means your execution, your iteration will be stopped. So, what will be the GCD of 12 and 33? That is 3, that is the value of a, it will return a. So, when we get the value of b is 0, that the a value will be the GCD. So, in example second we can see when we want the GCD of 750 and 900, same algorithm we can use. 900 will be divided by 750 and quotient will be 1, remainder will be 150, again b will act as a and remainder will act as b, and this iteration will executed till the b becomes 0 and returns a. Okay. In that case we can stop. Okay. Another example, if we want to find the GCD of 252 and 105, again we can divide 252 divided by 105 and we can get the quotient equal to 2, remainder equal to 42, and again that b value is assigned to a and remainder value is assigned to b, and that will execute it till the b value becomes 0, the return value, that is a, will be the GCD. So, what will be the pseudo code of Euclid algorithm? Prerequisite condition, what we assume, what are our assumption? We already assume that a is greater than b. So, in Euclid this is the like iterative, this is not the iterative approach, this is recursive approach. Here we already assume that a is greater than b, and when we have to return, when b equal to 0, then returns a. Else what we have to do, you have to execute Euclid algorithm, that is in place of a we have to you have to put the b, and in place of b you have to put the remainder, that is a modulo b. So, when we execute using this pseudo code, we have taken the example a equal to 50 and b equal to 12. So, GCD of a comma b, that is equal to GCD b comma a modulo b. When if we put the value of a equal to 50 and b equal to 12, the GCD next GCD what will be the GCD? That is we have to assign b value in a, that is 12, and what will be the remainder, that is 50 modulo 12, and we can get that is 2. Okay. So, again GCD of 12 2, that is GCD of 2 comma 12 modulo 2, that is GCD 2 comma 0. 2 comma 0 means 0 is the value b, and we can what will be the value of a, that is 2, and this 2 will be the GCD of 50 comma 12. Again we can see a value is 83 and b equal to 93 19. So, GCD of a comma b, that is GCD of b comma a modulo b, 83 comma 19. Again you can assign the b value to a, and 83 modulo 19, that is 7. Again 19 comma 7, we can get 7 comma 19 modulo 7. Similarly, at the end of when execute, when recursive call will end when b value becomes 0 and a will be the return. Okay. So, 83 and 19 both are the prime numbers. So, we can get 83 and 19 value equal to 1. So, these are the two approaches where we can use this GCD formula, that is this formula like non-recursive step, and this is the recursive step. Okay. So, in recursive approach GCD function is there, here 2 input m and n means both the numbers, and integer r is the remainder. This while loop will execute it till n becomes 0, n means value of b. So, we find the r equal to m modulo n, and that r value is assigned to n and n value is assigned to m, that will execute it till n becomes 0 and return m. This is the non-recursive step, and in recursive step already you have seen when GCD integer m comma n, that is if n equal to 0, then return m, else you have to execute n comma m modulo n. So, when we see the example of when we see the next example using like this formula, recursive formula. So, if m equal to 8 and n equal to 5, again that is if we want to find the value of r. So, r equal to m modulo n, that is we have to assign n value to m and r value to n. So, n equal to 5. So, r value 8 modulo 5. So, m equal to 5, n equal to 3. Again n equal to 3, r equal to 5 modulo 3. So, m equal to 3, n equal to 2. Again this process will be executed till n becomes 0, and what will be the value of GCD, that is 1, because m value equal to 1. In the case of like if we use that is iterative step 1 GCD 8 comma 5, that is GCD 5 comma 8 modulo 5. Okay. In the same way GCD 5 comma 3, in step 2 GCD 5 comma 3, GCD 3 comma 5 modulo 2. In the same way, when at the last step GCD 1 comma 2 modulo 1, that will become 0. So, 1 will be the answer. So, what will be the complexity analysis? How can in which case we will find the best case or worst case or average case? So, in case of in best case, if m equal to n, that 8 and 5 both are equal. So, then there will be only one iteration. Okay. If we say 8 comma GCD of 8 comma 8 means that is what will the value of r value become 0. R value become 0 means that value will be given to n. So, n equal to 0, m equal to 8. So, the final GCD will be 8. So, 8 comma 8 means 8 divide both of the number. So, 8 will be the answer. So, in that case only one iteration happen, that is constant time. So, big of 1. What is the scenario of worst case? So, the worst case of Euclid algorithm is when m and n are consecutive Fibonacci numbers. Fibonacci numbers, we already know Fibonacci series in which the next number is the sum of the previous two numbers. Okay. Here the example of Fibonacci number like 55 and 34, both are consecutive Fibonacci numbers. In iteration 1, here the m value equal to 55 and n value equal to 34. So, in next iteration what will be the n value? M value equal to 34 and n value equal to 21, because 55 modulo 34, that is 21. In iteration 2 similarly 34 modulo 21, and iteration 8 you can see in 8th iteration the n value equal to 0 and the m value equal to 1. So, that is your answer. So, this how many iteration will be there? So, number of iteration will be maximum in case of worst case, that is if both the numbers are Fibonacci series number, that is Fibonacci series number, and that will be the consecutive Fibonacci series number. So, in consecutive Fibonacci series number we can get the worst case time complexity. So, when n and m are the number of digits of a and b, assuming n greater than equal to m, then algorithm uses order of m division. So, in worst case we can say order of m division. Note that the complexity are always given in terms of the size of the input. So, in this case the number of digits. Okay. What will be the complexity in average case? Okay. In worst case order of m, that is you can say order of n also, that is linear time complexity. In average case the larger number is reduced by at least a factor of 2, because every time you have to calculate the modulo operations. So, if we assume that is each time it will be reduced by 2, then how many iteration will happen? That is log n, that is n equal to 2 to the power k, that is k equal to log n iteration. So, in average case by Euclid algorithm it is observed that GCD of m comma n equal to GCD of n comma m modulo n. Okay. So, GCD of m modulo n comma n modulo m modulo n. Similarly, we can see since m modulo n equal to r, such that m equal to n cube plus r, it follows if r is less than n, so m is greater than 2r. So, after every 2 iteration the large number is reduced by at least a factor of 2. So, there are at most order of log n iteration. So, complexity will be order of log n, where n is either the large or a smaller number. Okay. So, in average case we can get the log n complexity. In worst case we can get the order of n complexity, in best case we can get the order of 1, that is constant time complexity. So, next topic is Horner's rules for polynomial evaluation. How to evaluate the polynomial using the Horner's rules. Generally, how to evaluate the polynomial at a given point x. So, let us define the problem of polynomial evaluation. Consider the polynomial p x equal to a n x to the power n, a n minus 1 x to the power n minus 1 dot 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 a 1 x to the power 1, a 0 x to the power 0, where a 0 to a n are real numbers and we have to evaluate polynomial at a specific value for x. So, for example, p x equal to x square plus 3 x plus 2. This polynomial, quadratic polynomial, you have to find the value of x equal to 2. Okay. So, p 2 equal to, what will be the value of p 2, that is 2 square plus 3 into 2 plus 2, that is 12. So, now we will discuss Horner's methods for polynomial evaluation. What is the requirement of Horner's rule? We will see in later slides, because in general evaluation the time complexity will be higher, and if we use the Horner's rules, that time complexity will be reduced. So, consider the polynomial p x equal to a x square plus b x plus c, which can be rewritten as x into x a plus b plus c by using Horner's simplification. You can simplify any order polynomial using the Horner's rule. So, consider the polynomial p x equal to a x square plus b x plus c, and which can be written by this. Now, considering the general polynomial p x, that is a n x to the power n plus a n minus 1 x to the power n up to a 0 x 0, which can be rewritten, that is p x equal to a n x plus a n minus 1 into x plus a n minus 2 into x plus dot 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 plus a 1 into x plus a 0 by using the Horner simplification. If we use the Horner simplification, we can reduce the time complexity for evaluating any polynomial. Okay. So, now considering the general polynomial, and which can be rewritten by this, how to rewrite this polynomial using the Horner's, these are the algorithm. In step 1, pseudocode for polynomial evaluation, assign value of polynomial p, that is coefficient of nth term in the polynomial. Okay. So, the value of polynomial p equal to the coefficient of nth term, and set I equal to n minus 1, compute p equal to p into x plus a I, that we have to reduce, because I equal to n minus 1 and I equal to I minus 1, I minus minus, or you can say I equal minus 1. So, if I is greater than equal to 0, then go to step 4, that is, what is the step 4? P equal to p into x plus a I, and the final polynomial value at x is p. So, assume p equal to a n is the nth coefficient of nth term, and I equal to n minus 1. In the first iteration, what will be the value of p? So, p equal to p into x plus a n minus 1, that is a n into x plus a n minus 1. And the next iteration, when I equal to I minus minus, that is I equal to I minus 1, we can get I equal to n minus 2. In this case, p, what is the value of p? P equal to p into x plus a n minus 2 plus, that is equal to a n into x plus a n minus 1 into x plus a n minus 2. So, at finally, when I becomes 0, p equal to complete polynomial. So, we can see through example also. In step 2, algorithm to evaluate the polynomial at a given point x using the Horner's rule, input an array age 0 to n of coefficient of polynomial of degree n and a point x, output will be the value of polynomial at a given point x. So, how to evaluate and what will be the complexity? Evaluate Horner's, that is a is the array of the coefficient, n is the number, what is the power of like polynomial, and x will be the at what point you have to calculate the value of polynomial. So, p is the p equal to a n means the coefficient of highest power, that is a n, and you have to use the for loop, that is I equal to n minus 1 to 0 and I minus 1. Each time you have to decrease the value of I, and you can get the value of p, that is p into x plus a I, and return p. Okay. So, using this algorithm, what will be the time complexity? The time complexity of big O of n, because this for loop will execute n minus 1 to 0, And in earlier cases, that is like in layman approach, when we calculate the value of like any polynomial, we can have a worst case complexity big O of n square. So, big O of n square to big O of n, that is why we study the Horner's polynomial evaluation. So, what will be the time complexity? If we use the naive method, a naive way to evaluate a polynomial is to one by one evaluate all terms. First calculate x to the power n, multiply the value with a n, repeat the same step for other terms and return the sum. The time complexity of this approach is big O of n square if we use a simple loop for evaluation of x to the power n. Okay. And the time complexity can be improved order of n log n if we use big O of log n approach to evaluate x to the power n. In general, in naive approach, we have to calculate, because if a polynomial like a n x to the power n, that is x to the power n is a very big term. If we put the value of x equal to 2 and 2 to the power n, that will take already big O of n time. Somehow we can manage to solve this 2 to the power n up to big O of log n, and finally, if we have a n coefficients will be there. So, we can get the n log n, but in worst case we can get order of n square for naive method approach, naive approach. So, in case of Horner's method can evaluate polynomial in big O of n time. Is it clear? So, let us consider the example 2x cube minus 6x square plus 2x minus 1. We can write it as 2x minus 6 into x plus 2 into x minus 1. This is the simplification using the Horner's method. So, the idea is to initialize the result as the coefficient of x to the power n, that is here in this case coefficient of x to the power 3 is 2. Repeatedly multiply the result with x and add the next coefficient to the result, and finally return the result. Implementation of Horner's method. So, if we put the result equal to polynomial 0, that is you can say that value will be 2. So, for I equal to 1 to n, I plus plus, result equal to result into x plus polynomial I, and finally we can get the result. So, in this case the value of result, initial value of result equal to 2. So, if I equal to 1, that is polynomial I, that value will be minus 6. Okay. So, result will be result into x plus polynomial of I, and I value equal to 1. So, result equal to initial result value will be 2 to 2 into x plus polynomial poly I, that is poly 1, that is 6. So, this value will be 2x minus 6. So, initial result will be 2x minus 6. Again the value will be I equal to 2. So, result into x, what will the result value? 2x minus 6 into x plus poly I means poly I value will become 2. So, that value will be 2. So, 2x minus 6 into x plus 2. Again the value of I equal to like 0, 1, 2, 3, when the I value will be 3, that value will be minus 1. If we compare this 2x minus 6 plus 2 into x minus 1, that simplification we can get through the result. Okay. So, the time complexity is big O of n and the space complexity is big O of 1. So, here you can see the time complexity using the Horner's method. If we use this polynomial, like here the cubic polynomial is there, and we want to evaluate the value at x equal to 3. So, that x value will be assigned to this 3. First we have to evaluate. So, if we calculate that value at x equal to 3, 2x cube minus 6 square plus 2x minus 1, the value will be, if we put that value result equal to result into x. So, initial result value will be, what will be the value of result? Result will be 2, because poly 0 will be result, and the value of x, what will be the value of x? X will be 3. So, 2 into 3, and poly I means initial value equal to minus I equal to n, that is poly 1 value is equal to minus 6. So, 2 into 3 minus 6, that is 0. Again that result will be put into this. So, 0 into x, x value equal to, what will the value of x? X equal to 3, 0 into 3 plus poly I means poly value 2, poly value 2 means 2. So, what will be the value of result? That is 2, 0 into 3 plus 2, that is 2. Again in the similar way you can get the value of a result, and using the Horner's method we can finally evaluate that expression 2x cube minus 6 square plus 2x minus 1 at the given value x equal to 3. So, if we compare to the general polynomial evaluation, that is naive method, and this method or Horner's method, it simply indicates that at any cost we can get that polynomial evaluation in big O of n time, that is linear time. But in earlier cases, that is using naive method, we can get that polynomial evaluation in quadratic time. So, if we compare both the time complexity, which will be preferable? That is the Horner's method, that is big O of n, and the space complexity is also big O of 1. So, overall if I am conclude this lecture, so first you have to know the what will be the time complexity of the polynomial evaluation in naive method, and what will be the time complexity using the Horner's method. You can easily compare, and finally we get in naive method we can get the complexity in big O of n square time, and if you use the Horner's method, that complexity is big O of n, that is linear time. So, thank you so much.